In this example, you're going to learn how to calculate rainfall excess or Q in the SCS curve number method on composite area. A composite area is a study area that is consisted of different sub-watersheds or sub-basins. For example, in the photo that I have provided for you on this slide, you can see that there are multiple sub-basins: grass, parking lot, building, and retention area. So we have been asked to use SCS curve number and calculate rainfall excess or Q using two methods: distributed runoff approach and area weighted curve number approach. Distributed runoff approach is also called area weighted runoff approach. Although these two methods calculate rainfall excess, they are different. And let's talk about those differences. In method 1, distributed runoff approach, you calculate the total amount of runoff or total amount of rainfall excess from the watershed or from your study area as the summation of rainfall excess in every individual subbasin times a factor named alpha. And alpha for each subbasin is equal to the area of that subbasin divided by total area. That's why it's called area weighted runoff approach. So rainfall excess from each subbasin times that alpha I, which is the fraction of the total area represented by subbasin I. And I obviously changes from 1 to the total number of subbasins that you have. This approach tells you that calculate rainfall excess for every individual subbasin and then use the area weighted approach to calculate total rainfall excess. There is another approach that tells you, well, you can use the area weighted method to calculate an effective curve number for the entire study area and then use that effective curve number into the SCS curve number. In other words, it says that calculate an effective curve number is equal to curve number for each subbasin times the fraction of that subbasin. And again, alpha I is the same thing, is the fraction of subbasin I. So once you have this effective curve number, based on, depending on if you're using SI or US customary units, you can calculate effective watershed storage or S and put that into the equation of SCS curve number to find total runoff for your study area. So we're going to do the same thing, but in order to do that, first of all, we need to summarize the information that we have been given in this example. So I'm going to create a table with the information that I have been given. First of all, I know that we have multiple subbasins and every subbasin has an area. So this is the table that I'm going to create. Area of the subbasin. The subbasins are parking lot, building, open grass, and retention area. The areas have been given to me in hectares. Next, I need to calculate the fraction of every subbasin, or alpha I, which is dimensionless because it's area divided by area. I'm going to calculate the summation of areas and write it over here. The summation of areas would be 25 hectares. And now I can calculate alpha sub I. For the first one, for example, it would be 7.5 divided by 25 hectares, which is equal to 0.3. Similarly, I can write it for all others. Next, I'm going to write the given curve number in the problem statement, and curve number is also a dimensionless number. Based on this curve number, and the equation for watershed storage in SI. You can calculate watershed storage value, and it would be in millimeters because I use the SI equation. And eventually you're going to use the curve number equation to calculate Q and put it in the last column. Curve number equation, or rainfall excess, is 0 if the amount of precipitation is less than 0.2 s, and it is equal to this value if the amount of precipitation is larger than 0.2 s. Once you have SCS curve number equation, you can compute Q and write it in the last column. All right, now it's time to use the methods that we went through to figure out the value of total rainfall excess from the first method. And it's going to be this value times this value, this times this, and the summation of all of that. So I'm going to write it over here. The units is going to be millimeters because the unit for Q is millimeters. And from this method, surface runoff is calculated to be 145 millimeters. All right, now it's time to use the second approach, which is the area weighted curve number approach, to calculate surface runoff. So first we need to calculate effective curve number. And effective curve number can be written as this. It's alpha I times Cn sub I. So for the first subbasin is 0.3 times 98. And it is dimensionless because both alpha and curve number are dimensionless. Effective curve number can be calculated 81. All right, now we have the effective curve number. We need effective S, or watershed storage, to be able to put it into SCS curve number method. I'm writing the S equation for metric units, millimeters, and S will be 60 millimeters. Now that we have S, we can use the equation for Q, which is going to be, and S is the effective S. All right, putting all the numbers into this equation, the value of surface runoff is 143 millimeters. From the first approach, rainfall excess was calculated to be 145. From the second approach, curve number is calculated to be 143. This obviously means that these two methods are different. But what if I ask you which method is more accurate than the other one? Is it going to be the area weighted runoff approach or the area weighted curve number approach? The answer to that question is pretty easy actually, and you're going to say that it's going to be area weighted runoff approach, because when you are calculating runoff for smaller areas, you're going to calculate it based on specific curve number of that smaller subbasin, and then you will sum all the runoffs that are calculated. However, when you are calculating the effective curve number, that is the average curve number of the entire study area. So your number is not going to be as accurate as distributed runoff approach.